I was looking through my collection of interesting papers recently, and I came across this thing again, which took my interest. It looked fun. It's a nice provocative title, and decided to have a closer look at it. And I realised I'd read through it, but never really worked through the working out. So I wasn't too sure how the solution works. So I thought I'd go through that. I spent a little bit of time doing the working out earlier, so this should go fairly straightforwardly, but it's not going to go completely smoothly. I don't think. There'll be stuff I forget, but I just thought it would be fun to share this because it's a really nice thing to read. Very neat solution to a problem. So the setup is that you've got people seated around a table. So if we've got a table here, you've got, I don't know, some number of things. You've invited couples to a dinner party. You've got an even number of people. Everybody belongs to a couple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so I've already gone wrong. How do I should be able to erase with this pen. Nope. Nope. There we go. Right, okay. So now I need to pen. Here we go. So it's already not going very smoothly. Right, so that looks like 10 things. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Those are evenly spaced. It's not an accurate picture. So the problem is, how do you seat people around this table so that nobody is sitting next to their partner? And because this problem's quite old, the original formulation was, how do you sit it down with men and women alternating? Sometimes these days, you know, I've had dinner parties, there have been 2 men have turned up as a couple. Anyway, that's not the problem we're going to solve today. Well, we're going to solve that problem a little bit. So this is a classic thing, and there's a solution. It's a bit hard work. The abstract here gives a little bit of history about that solution, how he's not very happy with it. 1943, Kaplansky gave a proof of Touchard's formula. Kaplansky's derivation was simple but not quite straightforward, and the problem is still generally regarded to be tricky. So this paper claims to give a completely straightforward derivation of Touchard's formula. Touchard. Like Kaplansky's, our solution based on the principle of inclusion-exclusion. So this is a combinatorics problem. What did I actually say what the problem was? The problem is to count how many different ways of seating these people there are. Obviously there's a way, but the question is to count how many. So they're going to do that. This solution is really nice. I was quite wary when I first read it because I thought, oh god, combinatorics, I hate it. So we'll go through it. Yeah, what we'll do first is we'll go through it, just believe everything they claim, and see how neat it is, except not believe them because there's a lot of hidden work, and then we'll go and do the working out and discover why I can't do combinatorics professionally. Right, so first of all, first thing to do is to make the problem a little bit easier, which means there are fewer things to worry about to get the main thrust of the argument, I think. I think that's why we're doing this. So first of all, relax the problem so that we're just looking at the number of ways of seating couples around the table. So no one sits next to their partner, but we're not alternating men and women. So back at my table, I could have man here. We're still assuming that they're not part of the same couple, but anyway. So these are not part of the same couple. But really, this problem doesn't rely on there being such a thing as men and women, so we can have same-sex couples here. So the relaxed problem, relaxed in many more ways. So what we're looking for is, let's get my highlighter out. Can I do that? Yeah, so number mn, ways of seating couples around the circular table. So we're looking for mn, that's the thing we're going to count, the number of ways of seating couples around the table. what do they say? There are 2n factorial ways of seating the individuals around the table. So there are 2n people, n couples, 2n factorial permutations. That's straightforward. And use inclusion, exclusion on the set of couples who end up sitting together. Now this is where I start to get worried because I don't understand this very well. But the basic gist is you add in a load of things and then realize you added in some bits that you don't want, so you take those away. But then you're still not done, so you've got to add some more bits back in, and then you narrow it down, adding and taking away smaller and smaller numbers of things until you get to just the things you want. Everything that you want to keep has been added and taken away, well, an odd number of times, so it ends up added in. Everything you don't want ends up taken away. Okay. So let's do some more highlighting. WK is the number of seatings under which some specified set of K couples end up sitting together. So that means, suppose you've got, you know all your couples, you know all their names. So you say, this particular couple, I'm going to count the number of arrangements in which you sit together. Okay, or two couples, the number of arrangements in which they sit together. And then to get the whole solution, we say, well, it didn't matter which couples I picked to look at, so we count all the different ways of picking one couple or two couples or three couples, and multiply everything by that. Now the inclusion-exclusion part comes in. Hello? There we go. Yeah, right. Okay, so we've got couple A, B, C, D. I'm going to write, I'm going to do some arrangements down here. I'm going to write a 0 if they're not sitting together and a 1 if they are. So this one, that one, nobody's sitting with their partner. That one they are. That one C is sitting with their partner. And let's just make another one up. 1, 1, 0. Okay. So these are some of the possible arrangements. Okay, so in the first one, nobody's sitting together. In this one, couple D are sitting together. So if we were looking at all the arrangements in which couple D were sat together, that one would be counted, but not in any of the others. This one's the same, except we picked a different couple to sit together. And this one, C is sitting together, but also B is sitting together. So this one will count towards the one couple sitting together in two different ways, but that would also count for two couples sitting together once. There's only one way you can look at that and say that there's a particular set of two couples that are sitting together. Okay, so now there's this formula here, this thing. So the number of ways of sitting people around the table so that nobody's sitting with their partner is the sum of a k from 0 to the number of couples minus 1 to the k, meaning we're alternating adding and taking away. N choose k times the number of arrangements in which k particular couples sit together. So that is right over here. So that's W0 minus N choose 1 W1 plus N choose 2 W2 minus N choose 3 W3 ... and so on. So we're starting by counting the arrangements in which we don't care about any of the couples, what they're sitting together. This is absolutely everything. So I've got a specified set of no couples, and I want all the arrangements in which those no couples are sitting together. So that's what's that called? A vacant statement or something. So everything satisfies that. So every possible arrangement is counted in here. Then I'm taking away the ones that have one couple in. So actually, let's do some counting up here, because I found it quite useful to count along at the top with some arrangements. So everything gets plussed to start with as part of W0. And then the ones where a particular couple are sitting together, taken away. So that one's taken away. That one's taken away. Now this one, there are two ways you can get to this. You can say this couple are sitting together, so we take it away, but then we're multiplying by the number of ways of picking couples, so that means that we're also counting this one for a different reason. So we're saying that one plus somebody else is sitting together, so that one gets taken away as well. So we've taken away a little bit too much for this now, which is why we then add back in the W2s, so arrangements in which two particular couples are sitting together, and that happens once there. So we can see that, well, assume this works for all the others. I won't list them all. The one where nobody's sitting together ends up as a plus. These ones cancel out, and those cancel out. So that's how it's going to go. All the other arrangements are going to end up not counted, leaving only this, which is why this formula is the number of arrangements in which no couples are sitting together. There are tons of these, by the way. I've just said, are these things sitting together? There are lots of ways of making that happen. That's what we're trying to count. That's what we're trying to solve. So we need to work out a formula for these W's. But we'll do that in a bit. Okay, to finish the enumeration, we must compute WK. Assume n bigger than 1. If n is 1, it can't work because you've got date night. You've got a couple sitting around the table. They have to be on each other's sides. So that one doesn't work. N has to be bigger than 1. Fine. Okay. Let dk denote the number of ways of placing k non-overlapping unlabeled dominoes on two end vertices arranged in a circle. So we've got our two end vertices. Here's our diagram. And we're arranging dominoes, just meaning things that are too wide. So a domino covers up two spaces. The reason we're doing this is this domino could be that's a couple sitting next to each other. If a couple aren't sitting next to each other, if one's here and one's there, you can't stick a domino on top of them. So we're looking at all the different ways of putting k dominoes around a table, meaning k couples sitting together. Okay, so we'll assume we know how to work that out, which means we can then use that number. We haven't said who's sitting here or which couples these are, so for this arrangement there are lots of different ways of arranging the people. We have to pick all the different couples, and then we have to pick how we arrange the people who aren't in couples. So there are 4 people left, and there are I don't know, 4 factorial ways of arranging them. Okay, so that means the number of ways of arranging seating so that k couples are sitting together is the number of ways of sticking k dominoes around this thing times k factorial, meaning different ways of arranging the dominoes. So if we'd said couples 1, 2, and 3 are going to be the ones that are sitting together, then it could go 1, 2, 3, or it could go 3, 2, 1, or whatever. So all different ways of arranging those. Let's get rid of that. Yeah. Times 2 to the k. So for each domino, I get to pick, going clockwise, whether we have man first, then do I want to write W or F for woman or female? Let's say F. Either go MF or FM. Two ways of doing that. K time, I make that decision k times, so it's 2 to the k. Okay, and then finally, everybody else has to be arranged. There are 2n couples in total, 2k in the dominoes, so 2n minus 2k left, 2n minus 2k factorial ways of arranging them. Straightforward. Okay. Okay, so he explains that. So now we have only to compute the decays. This is a routine combinatorial problem. The answer is that. Right, so this is on our first run through. I'm just going to accept that formula. We will work out where it comes from later. See textbook that I can't get a copy of, or exercise 1 below. Exercise 1 is work out y. So yeah, that's not much help. Okay, so wk is equal to dk times all this. That simplifies down to that. Again, that's another thing we'll work out in a bit. Some suspicious stuff cancels out here. I mean, we've got funny factorial there, and ooh, yeah, where's 2n come from? Anyway, plugging this expression into the formula for mn above. So remember, we had it was minus 1 to the power of k times n choose k times wk. So we're sticking wk into this. We get that, so that's just stuck in, I think. Now this bit, I wasn't sure. I think this line, he's explaining why he's pulled that out, why he's known that that's something that comes out of this sum. I don't know, to make it easier to work out. I mean, we know n, so we can just work this out from this. It's not, we don't need any more insight to start computing numbers for mn. But he wants that to happen. So if you do that, you get this, and I don't know, that looks, we've got a 2n over 2n minus k back again. But then this really cool thing here, odd numbers up to 2n minus 2k minus 1 being multiplied together. So I mean, that doesn't look much easier to work out to me, but I don't know. We haven't even avoided factorials because, I mean, binomial coefficients have factorials in them. So anyway, we'll work that out next. So we've worked out the number of ways of arranging people around a table so that no couples are sitting together, but we're not alternating men and women. I was trying to think before what other ways of splitting up couples there are that don't rely on gender. There's oldest and youngest, but that's not, I mean, if you were talking to someone from that wasn't your partner, you wouldn't know whether they were the oldest or the youngest of their couple, assuming they're not sitting next to their partner. So yeah, I don't know if there are any ways of splitting people up that way. Right, so that's that. There's a sequence. It's probably in the OEIS. So mn over 2n factorial. This is the proportion of arrangements in which couples are not sitting next to each other. Weirdly, it goes down a bit, then it goes up a bit. Think about the asymptotics of that. When you've got absolutely tons, you'd be much less likely to sit next to your partner, wouldn't you? So maybe it tends to 1. Looks like a dinner party with 3 couples is the worst. Right. Okay, so there's that. And now we've got the slightly harder problem of alternating men and women. So I'll draw a table, and we've got da-di-da. I'll count this time. 1, 2, 3, 4, 5, 6, 7, 8. Do you like my table? There's some guacamole and some chips and things. Yeah. Actually, I need a different colour. Yes, I do. A different colour, says the colourblind man. Right. So we're going to alternate now. So we're alternating gender A, gender B, A, B, A, B, A, B. So there are n factorial ways of arranging these people and n factorial ways of arranging these people, and you get to choose which gender goes there and which gender goes there. So that's something. That's why we have 2 times n factorial squared arrangements. So that's how many arrangements there are, and we want to know how many of those have the property that no couple is sitting together. Okay, so again, it works just about the same as it did last time. Same formula, but we've got capitals because we're counting something different now. So the number of ways of seating people, n couples, and we're going to need to work out the number of ways of sitting people down so that k couples sit together, k particular couples, and we'll do the inclusion-exclusion thing. So for WK, the formula is slightly different this time. 2 is decide which are men's seats and which are women's. DK, that's the dominoes thing, so where the couples go. So a couple might go there, a couple might go there. So that's one thing that's counted by D2. Okay, so look at that one. Which couple goes where? So we've got 2 factorial ways of sorting those out there. So that's my k factorial. And where the n minus k men and n minus k women go. So we've taken away 2 couples, meaning there are 2 women left and 2 men left that we need to seat. So we arrange those, n minus k factorial squared. Got to do arrangements for both men and for women. Okay, so stick in the formula for the DK, which hasn't changed because that was just counting ways of arranging couples around the table. We get this thing. And I don't know, plug it in. So here we go, we get a thing which works. I think that's just straightforward subbing in. Why can I not? Yeah, there we go. Yeah, and then again, I don't know, it simplifies. This time the simplification is worthwhile. That was unnecessary. So by symmetry, we know that mn must be divisible by 2 times n factorial. So what does that mean? Suppose that we had labelled the couples. So we've got 1, 2, 3, 4, 5, 6, 7, 8. They always went in increasing order around the table. Or they went in order, I don't know. Then there are, well, that would count something. We could count that and then multiply that by n factorial to get the total number of arrangements. And those would all be different, so it's not an inclusion-exclusion thing. Then also, we could have just restricted ourselves to look at the cases where that's always men, and counted that, and then multiplied that by 2 to say, well, by symmetry, swap those around. So if we'd worked this out a different way, we would have had 2 times n factorial times something. So we know that 2n factorial divides the number of things we're counting, the number we're trying to get. So try and aim for pulling that out of the formula. And that's what they've done in this thing. Some more working out. So there we go, that's it. So it's really straightforward. Now, the reason this is interesting, which I think they'll say down here, Kaplanski's solution was, God, I didn't look into that much, but right, so I've done it again. Kaplanski's solution was, first of all, sit down all the women. So I'll say I'm going to sit these here. And then once you've done that, you've definitely not put any couples together yet, because all the couples are a man and a woman, and women are 2 apart. In fact, they're not all 2 apart. I lied. Have I done that? No. I'm terrible with this pen. I thought it had an eraser. I haven't set it up properly. Right. So, so yeah, you could have 2 women sitting together, which means that there needs to be a man there. That's tricky. Oh god, it's a slog. And then you work out where you can put your men in. So you know that this woman's here, her partner can't sit there, so he might sit here. Complicado. Whereas this one, we just did some inclusion exclusion, and we didn't really care who was a man and who was a woman. Apart from the fact there was a difference, so they had to alternate. But yeah. Oh, I couldn't have 2 women because they're alternating. Oops. Yeah. Okay, so that's why it's cool. It's non-sexist in that women don't have to sit down first. We can just tell everyone where to sit. Well, no. Yeah, we don't have that as one of the steps in our theoretical counting. This isn't a constructive way of getting an arrangement that sits people down, but we're not thinking about women first. Yeah, so that's that. So what he says, let's highlight that phrase. It appears it was only the tradition of seating the ladies first that made the ménage problem seem in any way difficult. We can dispute about whether it was in fact difficult even with this solution. I've glossed over a lot of stuff that was a bit tricky. But difficult here means difficult to someone who's good at combinatorics, I think. So what he said, what the gist of it was, Kaplanski's solution sits the women down and then anyway ends up doing the same sort of argument as they've just given up here. So it was a diversion that made things more tricky. Like how I said, what was my symmetry? If we'd worked things out, we would have got a factor of 2n factorial times something we don't know. That is possibly what happens with Kaplanski. I don't know. Yeah, so we've got some working out to do, just for completeness. So dominoes, first of all. No, dominoes later. Right, a number of ways of sitting these dominoes round. Now, I made some notes before, so I'm going to have to look these up. I'm not completely sure of this, by the way. So let's draw another table and put, I don't know, 8 things around it. Okay. So we've got 2n seats. We're going to sit down k couples. Oh, I remember what I did. Right. Let's erase these seats, or let's erase half of them. Okay. So what I came up with for this was we know that we want to put, for example, let's say we want to put 2 dominoes down here. What we could do is, oh no, there we go. I need 6 of them. I've got no, right. Let's look at a finished one. we could discount the clockwise way around seat of each domino, because knowing that that is the start place of a domino tells us that the one immediately clockwise around has to be the second part of that domino. So what we really need to do is take away k of the seats and pick k of them to be the start of a domino. So if I want to pick 2 seats here, I could maybe pick that one and that one, which means I have to put in a seat here and a seat here, and then they are dominoes. Okay, so that was 2n minus k places to start and pick k of them. There's my 2n minus k, choose k. Right, there's that. Now, why multiply by 2n over 2n minus k? Let's see if I can remember. Right, I think I've remembered what I was doing. So I need to have, what did I have? 6 of these. So 2n minus k ways of choosing these things, but I think you can rotate all this stuff around, and if that had been my solution, there's I don't know, I've started here, but I might as well have started there and had the same thing around. So I think everything's getting counted as many times as there are places to start, which is 2n minus k, so I need to divide by that. And finally, once I've done that and got all my seats in, I don't know, I think I need to multiply by 2n, because that's how many ways around there are. I'm not sure of this thing. I'm no good at combinatorics. Right, so we, I don't know, moderately happy with that. Right? I've got the 2n minus k thing, and then this, I don't know, it's something to do with that. I mean, it's a circle, so at some point we've got to talk about the fact that there's no start point of this, haven't we? Yeah. Right. So, got it right now. WK is dk times k factorial times 2 to the k times 2n minus 2k factorial, and we're going to need to simplify it to get this thing over here. So dk was 2n over 2. I wish I had a proper eraser on this. I need to set this up. 2n minus 2k, 2n minus k, choose k, times k factorial times 2 to the k times 2n minus 2k factorial, and let's expand out this binomial thing. 2n minus k. I don't want that. I want some brackets around this dude so that I can say 2n minus k factorial. K factorial 2n minus k is 2k factorial dot k factorial dot 2 to the k dot 2n minus 2k factorial. Look, stuff cancels. Wow. And in fact, we've got 2n minus k factorial and 2n minus k there, so that becomes 2n minus k minus 1 factorial. So we get 2n minus k minus 1 factorial times 2 to the k, which quad erat rearrangicum. Cool. And now stick that into the formula for n. That's just straightforwardly going in, so we just need to do this step to go from that line to that line. Find some space. Let's see if we can do it down here. So I'm going to look to get a factor of 2 to the n and n factorial out. Let's just look at, for a particular k, this thing, and forget about the sum for the moment. So we've got -1 to the k, expand the binomial thing, that's normally a good idea, times 2n times 2n minus k minus 1 factorial times 2 to the k. Right, now I reckon I want to, well, I'm trying to head for this 2n minus k choose k, which means I need a 2n minus k factorial on top, and a k factorial on the bottom, and a 2n minus 2k on the bottom. So I'm going to multiply and divide by 2n minus k. So I get -1 to the k, n factorial. I have potentially the angriest dog. Right, where was I up to? I was multiplying by 2n minus k all over n minus k factorial dot 2n, now divided by 2n minus k, and now I get my 2n minus k factorial from this thing, multiplying that by 2n minus k, times 2 to the k. Now, here's a tricky bit, and I'm going to need some more space, so I'm just going to get rid of all of that working. I know there's a quicker way of doing this, but so much more satisfying this way. Right. Okay. So I've got my 2n minus k factorial and my k factorial. I need 2n minus 2k factorial. Yes, that's what I need. So the thing to look at now is this suspicious thing. So 2n minus 2k factorial, that is 1.2.3.4 ... all the way up to 2n minus 2k. Let's rearrange that. 1.3.5 ... 2n minus 2k minus 1 times 2.4.6 ... 2n minus 2k, which is 1.3.5 ... thingamajig times, now these are all even numbers, so I can, and I've got n minus k of them, so I can pull 2 to the n minus k out of that. These are being multiplied together, remember, so it's 2 times 2 times 2 times 2. And then that is 1.2.3 ... up to n minus k. That is, frankly, a miracle. Because look, that is n minus k factorial. So 2n minus 2k factorial, let's write that down there. So if we have that thing and that thing and that thing, we can write 2n minus 2k factorial. Which means back over here, minus 1 to the k. N factorial is still there. Ignore that for the moment. Now my divided by n minus k factorial. let's write down my 2n minus 2k factorial. Do I mean that? No, I mean I want to write down, instead of 2n minus k factorial and k factorial, I'm going to write 2n minus k, choose k. I've accounted for that part and that part, but I haven't got a divide by 2n minus 2k factorial anywhere, so I need to multiply by that. And then I've still got my 2n over 2n minus k, and I've still got my multiply by 2 to the k. Let's draw a nice thick line dividing that from that, because I've used up too much space. Okay. That's the same as that. I pulled out, actually no it's not. There we go. I never got rid of my n minus k factorial. Okay. So now, instead of 2n minus 2k factorial, I'm going to write that thing I've got, and it's all going to work out beautifully. Minus 1 to the k, n factorial, 2n minus k, choose k. I'll write my 2n over 2n minus k as well. And my 2 to the k. Right, and now I've just got to write out this thing times, so that's 1.3.5 up to 2k minus 1 times 2 to the n minus k factorial, all divided by n minus k factorial from there. So that cancels, 2 to the k times 2 to the n minus k leaves me with just 2 to the n at the end. So I've got my thing. I can take out my 2 to the n and my n factorial, 2 to the n dot n factorial, minus 1 to the k, 2n minus, dear me, 2n over 2n minus k, 2n minus k, choose k, times 1.3.5. all that stuff, 2n minus 2k minus 1. There we go. So there's our factor of 2n n factorial to pull out. So this thing at the top works. Yeah, so I've lost the will to do the rearrangements for the other one, but it's basically the same. It's actually a little bit less tricky. So on the one hand, this is a really beautiful solution to this problem. You use one principle, inclusion exclusion, which if you've got an intuition for it, just goes straight ahead. If you don't, you have to do all that stuff with working out how many times stuff's getting included and excluded. These things are getting plus and minus in weird ways. That was what I had the most trouble with, working out why this thing gets taken away twice and then added on. But once you've done that, and you're an algebra whiz, you just stick some things in. The dk is apparently trivial. I don't believe it. And it all works out. So that's why it's a really nice, beautiful solution, but it's also hiding a whole load of absolute... oh, crikey, I pressed a button. There goes my rhetorical effect. It's hiding all this nonsense. Which took a lot of work and was just algebra, and there was, I don't know, maybe if you were really, really clear-sighted, you could give good counting intuitive arguments for all these operations I did, but really I was just using the rules of algebra. Yeah, but in the end it worked out. And actually, the formula we ended up with, that thing, not that pretty. It's not a pretty answer in the end. Yeah, but it's cool that you can answer these kinds of questions. That's why combinatorics is so powerful. These arguments, once you get them in your head, the particular way of thinking, it's very, very strong. And that's, I don't know, that's an interesting thing about maths, that there are these different fields that have such different ways of working, and they all end up being interrelated when some particularly brainy person manages to fit the tricks for two fields in their head at the same time and notice that there's a connection between each other. But like combinatorics works this way, analysis works by fiddling with bounds and wriggling inequalities all over the place, which is its own nightmare that I can't deal with. And group theory involves combinatorics quite a bit, but there's geometry going on and a whole set of other stuff. Algebra fiddling in a different sense. So, yeah, maths is a land of contrasts.